Hi. Today I plan to take the subject of derivatives. We have already learned limits to some extent, and now I am going to introduce the idea of derivative, and then we will follow it up with some examples, and I will also tell you why, and you will see why it is useful. Okay, so let's start. Okay, so we will talk about or I'm going to talk about the procedure of differentiation. We already talked about limits, and I hope you have seen the videos, or you already know the subject, or you are going to study on your own. Let's say why the idea of differentiation comes, and I will introduce you by giving an example of a hill. Okay, suppose you are going to climb a hill which looks like this. So on the y-axis I have the height of the hill, okay, and here on the x-axis some distance from some point O you are measuring. It doesn't matter which point, you decide some point O to be the origin, and then as you go along the distance is increasing from that point, and this gives you the height as a function of the distance. Okay, now if you are going to climb such a hill, you would like to know what is the slope at very different points, at various points, because it may cost you your life if you are not having that information beforehand. Suppose you are going like this and suddenly you walk down, and you know what will happen to you. So you want to know what the slope is at different points. Okay, so the question is to how we are going to find that slope, and that's what I'm going to talk about. Okay, so let's see how we are going to do. I give you a simpler example of a hill which will tell us how to determine slopes. Okay, and then we will successively improve that and make a real life hill, and we will know what procedure to apply. Let's say our hill looked like the following. Okay, let me look at my notes so that I don't spend much time. Yeah. So here it goes. I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. These may be kilometers or whatever you like. And 1, 2, 3, 4. Okay. And let's say our hill looks like this. It goes up to this place horizontally, then at 4 it acquires a value 3, then at 6 it falls down flat. Okay, it comes down like this. Let's say this is your hill, okay, which generally does not happen. You don't have such sharp things, but let's say this is. And if you want to know the slope at different places, it's very easy. The slope here is constant. It's a straight line. The slope here in this region is a constant. It will be different. And again, here it will be constant. How do you find that slope? So if I want to know the slope between O, let's call this point as A, this point as B, and this point as C. The slope is how much? You have already learned about the straight lines, so you know this. If I denote the height by f here, okay, it will be delta f over delta x. Okay, so you can take any 2 points on a line, it doesn't matter. So for example, you can take this. So what's the delta f? Delta f is 0. It is the value of function is 1 here, it's also 1 here. So between this it's 0. Delta x, let's say 2, it's 0. So slope is 0, which is what you know. It's horizontal, the slope is 0. So slope 1, let's say. So 1 meaning this, I want to call that this segment as segment 1. Let's look at the segment 2. Slope 2, again I should find out delta f over delta x. So let's say this is the final point 2, this is the point 1. So what's f? It's 3 here. 3 minus 1, 4 minus 2. Okay, if you don't know what I'm doing, then you have to read about lines and their slopes. So this is 2 over 2, it's 1. So the slope is 1. Okay, and it's positive, so it's a positive slope. And for this one, you know it will be a negative slope. Okay, it's negative slope, and you see also it is much more steeper than this one, so you expect the value of the slope to be negative and also higher than what you got here. Let's look at this. Here it is, function value is 0 minus, here it is 3 over 6 minus 4. It's minus 3 over 2, which is minus 1.5. Okay, so as I said, it's higher than this, but the value is negative. Okay, now let's take the case of a real hill. Okay, and if I want to know slope at any point, what should I do? Well, it's clear from this example what you should do. You can approximate this thing by straight lines. Okay, so let's divide this entire area into lots of small pieces. Okay, and then connect these points by straight lines. You see, it's good enough. Okay, it doesn't, the slope you get here is not really that good. These places it was better, okay, and so forth. Now if you find this, if you want to know the slope at this point, what you can do is you can take this point and that point and find the slope of this straight line which approximates this region of the hill. Okay, that will give you a good idea of what the slope is here. Similarly at any other point. Okay, and it's also clear, if you make a lot of divisions, very large number of divisions, then you will get a better and better approximation. And in the limit, you make infinite number of divisions. And if you want to know slope here, you take two lines very close and then approximate the slope. You will get a perfectly good result. So what we want to do is, let's look at this. Let's say I start with, I want to know the slope here. Okay, I start with these 2 points. The slope is needed here. Okay. So I take the value of the function, which is height here at this point, subtract from this value and divide by this, which will give me the slope of this line segment, right? Okay. Now if I bring this point here, then my estimate will get better. If I bring that point here, my estimate will get better. The more closer I get to the point P, the slope estimate becomes better and better. And in the limit, this point is becoming the point P itself, or the distance between these two. So let's say I bring it this point here. Now the difference between these two is, let's say the point P has value x, this one has x plus h. Okay, then how do I get the slope of this? F at x plus h minus f at x over h, right? That's the slope. And if I take this to very close to the x, I will have a perfect estimation of the slope. So I want to determine the slope of the line segment this small line segment here. In the limit, the distance, the points, these 2 points is vanishing. So I take the limit, h goes to 0. So we come back to the limits. Okay, so that's how we are going to find the slope at any point P. So I have told you that if I want to know, if I'm given, let's say, a hill whose height is given by f of x. Okay, so if you tell me the point x, I tell you the height which is given by f of x. Okay, then to know the slope at any x, what should I do? I should find out the value of x plus h, meaning if I want to know at x, find out the value at a point slightly further away, this direction or that direction, doesn't matter. Okay, subtract from it f of x and divide by delta x. What is delta x? Delta x is the difference between the values of those 2 points, which is h in this case, and then take the limit delta x going to 0. That gives you the slope, because this will be the slope of that tiny line segment. Okay, and in the limit this goes to 0, you get the slope, which you can also write as limit h going to 0. This is the same thing. Okay, I should, instead of writing h, I should have written delta x here. H doesn't make sense. Fx plus delta x. Now I've replaced, instead of delta x, h, and here it should be h. Okay, delta x is h. The gap between the 2 points is h. So that's your definition of slope. Okay. Now if f was not representing height or any other function, it could be, let's say it represents any function f, not necessarily height, it could be anything, whatever you like, then the same thing is what is called a derivative, meaning take a function f of x, okay, and if I want to know the derivative, which I denote by f prime of x, okay, so this is a new function. How do I get this? F prime of x, which I call the derivative of f of x, is limit delta x going to 0, f of x plus delta x minus f of x divided by delta x. Or if you write delta x as h, then the same thing becomes limit h going to 0, fx plus h minus f of x over h, which is this. This is called the derivative of the function f. Okay, this simple concept, and as you can understand, it's very useful because it tells you about the slope of a hill or the slope of a curve, and you may understand, I hope you understand what slope is. Slope is just how fast the function is changing at that point, right? Here, for example, function was not changing at all, it was 0. Slope was something, it was something else. So it tells you the rate of change of that function. So derivative tells you the rate of change of that function. And in the next video, I'll talk more about derivatives.